Imagine you're running a factory that produces two main products, exterior industrial paint and standard interior paint. When you look at the financials, you notice an immediate discrepancy. Your exterior paint yields a significantly higher profit per ton than the interior blend. Basic intuition suggests a simple strategy to maximize revenue. Stop making the interior paint and run the assembly line entirely on the high-margin exterior product. But physical reality gets in the way. You have a finite daily supply of chemical raw materials, and the market will only buy a specific maximum tonnage of exterior paint per day. If you pour all your resources into one product, you will eventually hit a raw material shortage or exhaust your daily buyer demand, leaving expensive assembly lines sitting completely idle. To navigate these exact physical and market limitations without halting production, operations managers rely on a mathematical framework called linear programming. Relying on guesswork to balance supply and demand in a constrained environment guarantees you will leave money on the table. A strict mathematical approach is essential to keep the factory running at absolute peak efficiency. The first step in linear programming is defining the ultimate goal, which mathematicians call the objective function. Here, maximizing our daily profit translates perfectly into a target equation. Maximize 5 times the exterior paint plus 4 times the interior paint. Next, you have to account for reality. Every limit on raw materials, labor hours, and market demand is written out as a mathematical inequality. These are your constraints. This graph visualizes how those equations intersect to form strict boundaries. Look at the downward sloping line representing the constraint 5x1 plus 3x2 equals 45. Anything beyond that specific line represents production that is physically impossible because you simply lack the required raw materials and labor. Focus on the shaded purple area trapped between these intersecting lines. This is the feasible region of mathematically valid production. By testing the extreme corners, we find point A yields our highest possible objective function value, 680. Maximizing output is never about pushing endlessly forward. It is about calculating the precise geometric edge of a system's physical limits. This framework is equally powerful when the goal reverses. Take the case of Ozark Farms, where the objective isn't about making a profit off a product, but minimizing the daily operational costs of feeding livestock. This table breaks down the farm's feedstuffs. Corn and soybean meal each have distinct protein levels, fiber contents, and costs per pound. Reading the requirements at the bottom, the final mixture must contain at least 30% protein, but cannot exceed 5% fiber. Those minimums and maximums create a brand new set of mathematical boundaries. The engine calculates the feasible region exactly as before, but instead of searching for the highest coordinate to maximize profit, it targets the lowest valid coordinate to minimize spending. Linear programming has no directional bias. It simply locates the extreme mathematical point that perfectly serves a company's specific objective. Drawing a graph works beautifully when a company makes 2 products, but modern supply chains manage hundreds of variables. The human brain simply cannot visualize a 20-dimensional graph, so this traditional geometric approach eventually hits a hard wall. To solve this, mathematicians developed the simplex method. This tableau crunches multivariable constraints purely through algebra, eliminating physical shapes. By tracking the ratio column and entering variables, the algorithm systematically tests mathematical intersections, pivoting corner to corner until an optimal solution is proven. Today, no one calculates these matrices by hand. This interface shows the solver tool operating directly within Excel. By pointing the set objective field to your profit cell and mapping limits into the constraints box, the software automates the entire method in milliseconds. Complex constraint mathematics used to require a room full of statisticians. Now, that optimization engine sits quietly on nearly every standard office computer in the world. Expand these principles past local farms and individual factories, and you see how linear programming governs the global infrastructure we rely on every day. Passenger airlines map flight crew schedules using these precise models, juggling FAA regulations and daily routes to minimize idle time across a global workforce. Massive package delivery networks route fleets of trucks using the identical math. They balance fuel capacities, vehicle weights, and tight delivery windows to minimize their daily diesel burn. Look at any major modern supply chain and you will see apparent chaos. But underneath the surface of all that moving freight is a strictly balanced, perfectly solved inequality. In a world built entirely on finite resources, perfect business strategy is not an art form, it is an equation.